to present one second. Yeah, so the other two people have not joined. I think again there's some confusion about 9 p.m. thing. I don't know. I send mails. If they don't see the mails, then I don't know what to say. Anyways, let's start. Yeah. Yes, but no, but I'll do that. Okay, maybe I'll do that in the end because today's topic is completely different. Today we will not need it at all, but certainly I will mention it to you. We use the greedy method in Wednesday's class and in Saturday's class which you are attending. We'll yeah, but I'll say it in the end. Today I just have planned certain things, so let me start with that. Um, one second. Yeah. So the question was of adding. This is what we were doing. So I think there is some confusion. Two people I think there is 9 at 9 p.m. So they have not joined. So that's why I was just asking them. Yeah. In any ways, yeah. So what we are trying to understand, this is just a quick recap. Okay, is adding recap of this topic. So we were trying to add. So here I'll put this in, quotes, because that's, you cannot really add infinitely many things, but in some sense you can. Okay, adding infinitely many numbers. So that's what we are trying to do. We are trying to add infinitely many numbers and trying to understand, what happens to the sum. Does it blow up and become infinite, or does it remain bounded? Okay, so how do you interpret this? What does adding infinitely many even mean? Okay, let's just take an example. Let's take the very first example that we had seen, which I suppose all of you know. But let's try to understand what it means to ask, what it means to say add infinitely many things. So it is basically like you start with the number one, then with one you add half to it, and then you add a 1 by square to it, and so on. So essentially at each stage you're adding one more number, right? So after, let's say, 100 steps, you would have added 100 numbers. Okay, so after any, and at any, I mean, infinity is a fake thing. Infinity doesn't really exist. Okay, it is just to try to understand what happens when you add many and many things. Okay, when you add large number of things and you're just trying to estimate what happens, what does the sum then roughly look like? Okay, so we are trying to understand what does, where do these numbers go? Do they go to some particular number? Do they get closer and closer to some number as you add more and more numbers? Okay, dot dot dot. So the question really was, what happens when you add more and more numbers? Where does the final thing go to? Does it? So the question was, uh, is I mean, question is, are all these summations? These are all finite summations, right? Are all these summations bounded? Bounded again means, are they, are they bounded by some number above? Like, are all, is there a number such that all of these are less than that? Okay, bounded by a fixed number, right? And we need a fixed number because obviously at each stage it's finite. So at each stage it's a finite number, so obviously it's a fixed, it's bounded by that, it's bounded by that number. But we want one number which will take care of all these summations. As you add more and more, still, no matter how many you add, you will still remain less than a particular number. Okay. That was really the question. Or does, what's the other way? I mean, the other thing is that it just blows up, it just becomes bigger and bigger than any number. Okay, these are the two things that can happen. So in this case, certainly the answer is, in this case the answer to this question is yes. Yeah, we had seen this, that the answer to this question is yes. And in fact, we even found out what the answer was, right? I mean, uh, these things tend to 2, right? These summations, as you keep adding more and more, so maybe you can say like this, if we just keep adding, then this, we say that it is 2 because it just goes closer and closer to 2. So can anybody give an explanation of why this happens without using some maybe formula if you know it? Without using any formula, can we give an explanation as to why this thing, this sequence, this series uh, is roughly 2 as you add more and more numbers? Or why is it at least less than equal to 2? How can you at least explain that? So that's the question. How do we explain that this is less than equal to 2? So we had used the geometric method. Is that right? We had used the geometric method to understand, or to prove rather, that this is less than equal to 2. Can anybody, yeah, come up or explain that? So what we are asking is a geometric maybe explanation as to why no matter how many numbers you add here, this will still remain less than equal to 2 and get closer and closer to 2. Yes, yes, something like that. Yeah. That's right. That's briefly the summary of it. That's right. So let me say the details. So in this case, it will be particularly simple because the number is just half. Since the number is half, it won't be a complicated explanation because, I mean, look, if this number is half, you can just divide this, right? And this area is half. That's clearly half, right? So we are bisecting the square horizontally. What do we do in the next step? Okay, so I'm sorry, there's a square here. So there is a square here. So how do I get 1 by 4? Obviously, I will just bisect this side. Right? This is already half, and this is also half. So you get a 1 by 4, and you can continue. This is very simple. You can just continue, and so you understand that eventually you are going to fill up the square, or to really say it precisely, as you add more and more numbers, you are leaving lesser and lesser area of the square remaining, and that lesser really goes down to 0. Okay, so just complete the detail. This is very simple, very simple. Okay, now, but this is very simple. We want to actually answer proper question, which is, well, this was when it was half, then these numbers are less than equal to 2, and they are, no, and the sum is tending towards 2. And so that's what we say when, that's what we mean when we say that if you add infinitely many, all of them, then it becomes 2. Okay, but in any case, I'm not making that precise. This is informative because the precise way will be calculus, which we will, limits will be the notion of limits, which we do not want to introduce now. Okay. What we really want to do, what we really want to do is, let's say the following question. Okay, we take 2 by 3. So we take 2 by 3, and then you have 2 by 3 square, you have 2 by 3 cubed, and so on. And we are asking the same question. when you add infinitely many of these, what happens? Or as you add more and more of these, what happens? Does it remain less than a number? Does it blow up? What happens? So here, certainly there is an algebraic way. Okay. There is an algebraic technique. This is known as a geometric progression, and there is an algebraic technique. There is actually a formula which one can use. We will discuss that, and also the technique behind it, and then we will try to use it in more non-trivial ways. That's a technique. That's a technique on its own. It's a very useful technique. But we want to see something which is useful and at the same time more fascinating, maybe beautiful. This is also fascinating. In fact, both of them are the same techniques. One is in pictures and one is. We'll try to understand that. We want to show that this sum is less than sum m. No matter how many of them you add, it will still be less than sum m. That's what our goal is. Okay. How are we going to do it? That is a question. Yeah. So if someone has worked out, because I had given the recipe for this the last time, has anyone worked out the details? Yes, Aritro, the class started at 8:45. I had sent a mail, but anyways, this is where we were last time, or more or less. Well, I started at 8:50. Yeah. In any case, yeah. So has anybody worked out the recipe for the geometric proof? And so it's not just mere memorization, of course. It's not memorization. It's not memorization at all. There's a certain thing. If you understand that, then you remember. Otherwise, you'll forget it mostly. Yeah. What's the geometric way? I would just say. What's the geometric way? So let's see. Okay. Let me remove these things a little bit. Let me remove this also. It's quite a fascinating method. We once again start with the unit square. It's a bit counterintuitive because this summation is not less than 1. If you add a few terms, you will see that it becomes more than 1. Yes, it's not less than 1. But still we are using a unit square. Let's see how. Start with the unit square and we'll do the following. Okay, we will cut it at a point. Maybe this is certainly not correct. It's 2 by 3, so it's more than half. We will cut it at this point where this is 2 by 3. Okay, now I'm going to erect a square of side 2 by 3. You see, I have chosen 2 by 3 for a specific reason. If you choose 1 by 3, then there is nothing to answer, because if 1 by 2, 1 by 2 square, 1 by 2 cube, if that is finite, then 1 by 3, 1 by 3 square, and so on will obviously be finite. There is no question because it's lesser. 1 by 3 is lesser than 1 by 2 and so on. This I had said the last time. So yeah. So then we have erected a square here, which is side length 2 by 3. So you see 2 by 3 square has come in the picture. 2 by 3 has not come because we are going to calculate the areas, right? 2 by 3 has come in the picture. 2 by 3 square we don't have. This is the 2 by 3 square. 2 by 3 we don't have. Yeah. Okay, what should we do next? So let's see. If this thing is a square, yeah, this thing here, I'm not putting labels because 2 by 3, the thing is a square. Yeah, Then the following is also a square. This top right corner, I mean, doesn't look like a square maybe, but it's a square, right? It's a square because this is going to be 1 over 3. Sorry, yeah, this is going to be 1 over 3, and this is also going to be 1 over 3. Sorry for the bad diagram. Okay. If anybody wants, I'll change it now, but otherwise I think it's okay. 1 over 3 and 1 over 3. Okay. Now try to think of this like this. Okay. You had a square with side length 1. Okay. That square had a square inside it which had side length 2 by 3. Okay. We had a square of side length 1. It had a square inside it of side length 2 by 3. This is a square of side length 1 by 3. Okay. So it is 1/3 of the bigger square. Let me use labels, I think, because I'll write a bit also. Because one should really get the idea of this. This is a fractal homothetic kind of ideas which will be used in many places. So C, E, F, G maybe. Okay. So FBGE is 1/3 of ABCD in all senses. I mean, yeah, not area is 1/9, but in any case, it's 1/3. Side lengths are 1/3. But we want to say a bit more. We want to also transform this square and see where it goes in that 1/3 world. In when you have zoomed out by 1/3. Okay. I mean, if you zoom out by 1/3 everything, okay, then ABCD goes to FPGE. But then the square, maybe HI, this square, this 2/3 square, that also goes into that, right? And what will be the dimensions? Can anybody tell? If it goes in, then what should be the natural side length of this smallest square that you see? Maybe it is a different color, maybe. No, 1 second. Let me just, otherwise it'll just keep getting more and more skewed. Let's say it is this. Yeah. So if this square transforms to this square, HEID transforms to this green square, then what should be the dimension of the green square? What should be the side length? 2 by 9. That's right. Yeah, because everything becomes 1/3, and that is the idea. You see, everything becomes, so it's like inside this square you have a smaller world, which is just a smaller world of the bigger world. Okay, so it's just there. Right. Yeah. So it becomes 2 by 9. Side length 2 by 9. But you know that this will continue. Yeah, it's like I've seen this thing when you're sitting in a saloon, right? You have mirrors on both the sides, and you can see the mirror inside the mirror, and then inside that you see, it's something like that, right? I mean, you can. I don't have a concrete model, but this thing happens. No, okay. So right. I mean, so now if you have this inside the big square, okay, then that will also get transformed, right? If you take another square here, and what will be the side length of this? Let's try to understand. This is a square, this yellow orange thing. This will be 1/3 minus 2/9, right? That will be 4 by 9, right? So this will be 4 by 9, and this is also 4 by 9. And let's answer this question again. If I make the blue square, what should be the side length of the blue square? You see, so the initial square, which was this was 2/3, we went, it became, this green one was 1/3 of that, so it became 2/9, right? So naturally the next one should be 1/3 of that, isn't that right? It should be 2/27, right? So this should be 2/27, this side length, because once again it will just be 1/3. Yeah, so maybe let's try to understand that in a different way. So this is the blue. Let me remove this blue. Yeah, so how can we understand? Yeah, let us name things again: x, y, z. Okay, and maybe w and y. I mean, it's intuitively clear what I said, but let's just maybe rigorously test it. So FBGE, okay, the side lengths of FBGE are 1/3. The side lengths are 1/3. And okay, 1 second. So if this is 1/3, wait a minute. So if this, yeah, so the whole thing was 1, and we took 2/3 of it, and we were remaining with 1/3, right? And so EG was 1/3, FE was 1/3. Yeah, till there it was fine, right? Then this 2/3 square, that also will become 1/3, so it will become 2/9. So it just became 1/3 of it. But now 2/9, right? 2/9 divided by 1/3. Okay, 1 second. It's not becoming 1. So if this, yes, that's right. That's why I said 2/27. Yeah, right. But one has to explain this more clearly, maybe. That's what I was saying. This should be 2/27. It is 2/27, but just based on, because it's just becoming 1/3 of what it was, so it's 1/3 of 2/9, so it's 2/27, the blue square. But to explain it more clearly, I mean, if this was, so if this is 1/3 and this is 2/9, and if you are sending 1/3 to 4/9, one has to, so if 1/3 is going to 4/9, right? If 1/3 is going to 4/9, so then it means that one is going to just one is going to 4/3. What? Wait. 1 second now. So wait. No. This is there's some mistake that I'm making, right? So, well, intuitively, I mean, the way we explained it, it was okay, but this way is getting a little confusing. Right. So the whole thing is, this whole thing is 1/3, and from there we remove 2/9. So let's just check this again. This is maybe this is where it is wrong, right? That's why I'm getting confused, because this will be 3/9 and this is 2/9. It is 1/9. That's why the whole confusion is coming. That's what I was thinking. That's why, like, from one angle it's coming and the other angle was not coming. It's 1/9. Yeah. Now it's clear, right? From 1 you go to 1/3 and then you go to 1/9, and so this will also become 1/3 of, because 1/9 is 1/3 of 1/3, right? And so this green square, which is 2/9, also becomes 1/3 of that, which becomes 2/27. Yeah, now I suppose it is very obvious. Okay. Just try to work this out again on your own and try to write it. Okay, if you want, you can show it to me also, but try to write it. The whole problem was happening because I made a wrong calculation. I don't know why I wrote 4/9. Certainly not 4/9. Yeah. In any case, what are the areas? Let's now just come to the areas. If this is clear, this is not just it's not just mere calculations, right? It's something neat. So we have 4/9, and let me just write that the first area, right? The first area is 2/3 square. I mean, the area of this square, right, is 2/3 square. And then the area of the next one, the green one, area of the green one, right? What is this? That is 2/9 square. Yeah, is that right? It's 2/9. One second. It is so if this is 2/3 and it's 2/3 square, then this is 2/9 square, right? And the next one is 2/27 squared. The areas, right? I mean the areas of these squares. That's what these things are. Are these things? Okay, but this was not the series that we are interested in. This series is somewhat different, right? Series is somewhat different. But let's see. Let's not get disheartened here. This is what we are getting. If you actually try to arrange it, so these are the areas, right? And all these areas are certainly sitting inside this unit square, right? And also the point is that this will never end. You can keep going, because if you have this, then you're taking the square you take is 1/9 of that. And so at each stage, the corner square that you draw in each smaller square, the corner square will be 1/3. So you'll always have space for the next square and next square. So what do we get? What kind of series are we getting? So we have proved that this is less than 1, right? But let's see what this is. This is the 4 is there. That's fine. That's there. But then we have 1/3 square, 1/3 to the power 4, 1/3 to the power 6, and so on, right? That's what we are getting. And we proved that this is less than 1. But this is not what we want set out to do. So how do we make adjustments and uh, comment on something about 2/3? Right? We need to comment on something about 2/3, not about 1/3. So how can we adjust? So sorry, this was, yeah, this is 2/3. So it's very simple, because I mean, see, when you took 2/3 here, right? When you took 2/3 here, then you are getting 1/3 here, right? So 1 minute. Yes, right. That's right. So what you should be doing, I think about this. When you took 2/3, then the remaining part was 1/3. And so every time you are multiplying by 1/3 square, right? From here to here, you're multiplying by 1/3 square, and you're multiplying by 1/3 square. How is that 1/3 square coming? Where is that coming from? It's coming because you're shrinking by 1/3 every time. Is that right? So I'm just seeing how you can make mistakes, or how you can make an attempt to a problem and this will not work maybe, but then you realize what adjustment you need to make. Okay, so first question, you realize that it's not working. This is not what we have want, precisely speaking, right? But it's quite close. My point is that we took the side length of the square to be 2/3. This square was 2/3. Because it was 2/3, and because it was 1/3 because the remaining was 1/3 of the square of the unit square, we ended up multiplying by 1/3 to the side, and so 1/3 square to the area. And then it continued like that. And so at each stage, you had 1/3 square, 1/3 square, 1/3 square, and so on. It went like that, right? Now you change the situation. You just change the situation, right? If you make this 1/3, if you make this square 1/3, and you should work out the details here. Yeah, if you change this to 1/3, then you will get, then the series will become 2/3, 2/3, right? Because then the first one will be maybe 1/3. The first, instead of 2/3 square, it will be 1/3 square. But now this square is 2/3, not 1/3. Just 1/3 and 2/3 get flipped here, right? You try to see that, right? And so, I mean, the next time it will not be 2/9, but it will be 2/3 of 1/3 and square of this. And then next step, it will be again 2/3 of the previous thing. That is 2/3 of 1/3, 2/3 of 2/3 of 1/3, and this square. You see, then the 2/3 square things will start appearing. I think it's good that we made this mistake. Yeah, then now work out the details. Yeah, work out the details that if this is 1/3, then it works. Not when it is 2/3. Okay. Right. So that's what it is. So are there any questions? Okay, no questions. So is the construction clear? Okay, and you have to take 1/3 to go about it. Yeah, right. But then what will you end up showing? I mean, if you really do this, then you would not, again there is a problem. Again, it's not done. The issue is that you would end up showing, see, remember, right? You were just getting this. You are not getting the odd powers. We got that this is finite. I mean, not just finite, it's going to be less than 1. Or maybe 1/3 was there, something will be here, you get multiplied. But in any case, I mean, it will be less than some, let's say 10. That's, yeah, something like that. But then how do you, but we didn't want to show this, right? We wanted to show something else. We wanted to show about, um, yeah, we wanted to show about um, this. So how do we comment on this from here? And this is again a good technique. So it's like an associated series. So how do we comment on this geometric series from what we have done? Hmm. Any ideas? Okay. We do. See, these are all the even powers. And here we need all the powers. So you can separate this. You can, because this is accumulating things, right? So you can, as you're accumulating, you can put them into two boxes. Here you can keep the even powers. And now this is very more or less easy thing. You've kept the even powers here. Maybe you can write one more and so on. And here in this bag, you're keeping the odd powers, which is also what you need to be able to comment on, right? you need to comment on what happens to the sum. Now try to think. We've shown that this is less than something, that you can work out the exact number or the bound, but yeah, this is what we have shown. So what do you do with these odd powers? Can you connect it with the even powers? Let's think about that maybe. Can we, yeah, can we connect it with the even powers? Yes, right? We can certainly connect. You just need to take out a 2 by 3. Just take out a 2 by 3. And then it just becomes even powers, right? That's it. And you know that this is also finite. You know this is less than 10, maybe something, figure out. So the whole thing will be less than 2 by 3 plus 10, and then a 10 here. But again, it will be finite. This is a very important technique, right? From knowing only the even powers or knowing only the powers which are multiples of 3, maybe those variations can be given, right? Then you separate it into pieces, and then, well, one piece will be what you already have, and from the other pieces you can, factor out some suitable thing and convert it to what you already have. Okay, that is the thing. That is the approach. Now try to understand that. Yeah, that's very important. Let me just give you a couple of problems which you guys can just try out with this. I mean, obviously here already you have to work out the details, and here there's that, show that for any r, show that for any r less than 1. So my point is that you can work this same proof for any r that is less than 1. This is nothing. Once again, now there is nothing special about 2 by 3 or 1 by 3, as you can understand. For any r less than 1, show that, once again, show that if r is less than 1, then 1 plus r plus r square plus r cube and so on is finite. Okay. Once again, I mean, you will not get this directly. You will get something like maybe r square, r to the power 4, r to the power 6 is finite, and so on. But what is more amazing is that, see, here you have shown that it is finite, and that is good. But what we want, if we can, is to know the exact answer. Where does it actually go? Like, what is the actual summation? See, 99% of the times in this subject of series, you will not know the exact answer. Okay, maybe that's what a few, like the sequence chapters from the textbooks might tell you maybe sometimes. But eventually, when you're doing limits and calculus sequences there, then most of the times you would not know what the actual answer is, but you'll develop techniques to show that it's finite. Okay, so in this case, you've shown it is finite, but in this case, exact answer can be found. And I think maybe if someone has done geometric series and they would know what the answer is. But let's see. The exact answer can be found out. But more than that, the exact answer can be found out from the picture. Now this detail you have to try to do from the picture. So if you think about it, if you look at this picture that we had, So this time just drawing it like this. I mean, I use this picture to just show that the sum is finite, right? But in fact, you can use this picture to actually find the sum. Okay, and that I'm not going to say. Okay, I mean, in fact, I have to also think about it. That's the reason I'm not saying. But it can be done. So what I want guys to do is to use this picture. I mean, there are more things to draw, but use the picture to actually find the answer. Okay, use the picture to actually find the answer. And let me tell you what the answer is, and we will also derive the answer in an algebraic way. Okay, the answer to this is going to be very simple. In fact, it's just 1 by 1 minus r. Okay, the answer is just this. Is that right? Yeah, the answer is just this. It's just 1 by 1 minus r. So how is it proved? How do we know that this is 1 by 1 minus r? Anyone knows the technique? Pictorially, you have to think. Now that you know the answer, you may be able to do it more easily. But we want to first show it algebraically. How do we algebraically show that this is 1 by 1 minus r? In other words, it's very interesting that if you multiply this, if you, and that's how maybe you can pictorially also get the answer. It's 1. Okay, so if you just look at it more closely, it is like this 1 minus r times r square 1 minus r times r cube is equal to 1. So this is like the area of the unit square. It's like the area of the unit square, and we are splitting it like this, and that you have to figure out from this picture. Okay, that you have to figure out from this picture. But let's prove this in a different way. Okay, let's prove this in a different way, and the picture one you can try to prove it later on. That will take a bit more thinking, and if I tell just the solution, then it's not fun, I think. Yeah. But the idea of the idea of the pictorial proof really is, right, you take a quantity and you kind of, you know you kind of shift it and you find the same you take a shape or you take a structure and you find the same structure inside the structure itself as as a substructure. Okay, so you have some shape which we had, and inside that same shape we had the same thing again, and then kind of a fractal. Yeah. So that's what it is. Right. So now we want to look at the algebraic proof. That's also, I think, pretty standard and pretty important. Algebraic way. But from the algebraic way, we will actually prove much more. We will prove much more than just this formula. And let's see how we can do that. So, I mean, it just starts with something very basic, and that is you just take 1, 2, 2 square, 2 cube. I mean, if you just play around with these numbers, you will see a pattern. When you try to add 1 plus 2 and then 1 plus 2 plus 2 square, when you add those numbers, you see some pattern, and you will see that it is like this. When you add the first, n powers of 2, you actually get the n plus 1th power of 2, but just one less than the n plus 1th power of 2. Okay, this is something that you can easily, check. Just try to take a few numbers and check this, and if you already know it, then that's very good. But it is, in fact, what is true, and let's not prove it right now because I just want to do some other stuff also, and meanwhile you can try this. It's a very standard thing, is that this is like this. And I'm saying that you can just prove this without using any induction, or just, I mean, rigorous proof will need induction, but just take an n and try to prove this. Okay, How do you prove this? Just take this side and cross, just multiply out and just check that everything cancels out and only r to the power n plus 1 is remaining. Okay, so just check it. Just check this. There are more illuminating proofs, but right now let's just check this. I means for now try to just check it. And also the geometric proof is there, but that's for the infinite case. This is what you have. So what does it say? What does it? If you assume this equation, if you assume that this is true, okay, which also is similar to this, which is very easy to see. If this equation is true, then if r is less than 1, so if you want to understand what happens to this summation when n becomes very big, is that right? Yeah. So when n becomes very big, right, as you make n bigger and bigger, so if r is less than 1 and n becomes bigger and bigger, then r to the power n plus 1 kind of goes to 0, right? No matter how big the, I mean, r may be 99 by 100, but still, if you make the n big, then 99 by 100 to the power big power will become very close to 0. And you can make it as close to 0 as you please by making the n big enough, right? So the point is that when n becomes big, as n becomes big, just a rough explanation, then this quantity kind of just loses its significance. But more than that is that you can make it as insignificant as you want by taking n big enough. That is really what the thing is, okay? Right, and so that basically just becomes 0 if you add infinitely many terms. That's what we say. It becomes 0. Then this quantity just is 1 by 1 minus r. Okay. Really speaking, it is as close to 1 by 1 minus r as you want, but that's what we mean in the limit that it is 1 by 1 minus r. Okay. So is that good then? Yeah, this is the formula. This is the geometric formula for the finite case. We'll prove this the next time if, yeah, we need to, and we see the geometric proof of the geometric progression, then we'll see this proof, and we already have the infinite version then follows very easily. Okay, so this series will be pivotal, right? We will be using this series all the time to compare with others. If we want to test for some other series, then we will compare it with this series. So we will use the fact that this series converges. Okay, this r square, this, when you add these, then its summation is finite. We will be using that to comment on other series, whether they sum up to finite or they don't sum up to finite. That will be the thing. Okay, and those are the techniques which we want to look at, okay, intuitively at least. So yeah, let's do one problem which I had asked last time. uh, let's see. It was this: if you take something like square root of 1 times 2, and then you add to it square root of 2 times 3, and then you add to it square root of 3 times 4, and so on. If you keep adding these things, then does the summation remain lesser than some number, or does it become bigger than any number you want if you take enough terms? So has anybody tried this? I think I had this question last time. That will not help. Will that help? Because, okay, if you rationalize, let's see. Yeah, if you rationalize, then what happens? You get something like this. Because it's very simple to rationalize, but will this help? Sorry. Yeah, might help. We have to see. So can we say that this will remain less than some number, like the geometric case, that like the previous case, or will this blow up and become bigger and bigger? Okay, as a hint, I think we should have we would have tried it already, but as a hint, we will try to use the fact, and this is something which we had shown the last time or last to last time, using geometric progression for half. Use the fact that this, and for those who don't know how to do this yet, try this. Try to show that this thing, as slow as it might look, this is infinite. What does it mean? It means that if you want this series to become more than 100, you have to just take enough terms and it will become more than 100. If you want it to become more than 1000, it will become if you take a few more, if you take more terms. So this series doesn't remain less than any number. It just becomes bigger and bigger, and it becomes bigger than any number you want. Okay. Try to, so for those who don't know how to do this, try to prove this. And for the time being, let's assume this is true. And then what can we say about our question? Any guesses? If you, mhm. ah, you, okay, okay. So then what? Hmm. Right. So then what's your conclusion? Uh, right, right. So it should be infinite, right? Yeah. So roughly that makes sense. You can also say it more directly. At least you will not have a proof maybe by this, but intuitively you can do this. Try to and this is a very important technique. Okay, compare the nth terms of the two series. So there's a notion of similarity of series, which we will see concretely later on. But here, you look at this term and you look at this term and you try to compare them. Aren't they more or less the same things? Right? If you look at this, or you look at this, don't you think that these two are more or less the same things? This is like square, this is like n square mostly. See, when n becomes big, right? When n they are right, when n becomes big, then this plus one really loses its significance. You can think of in those terms and think more in those terms, and you can be more convinced. But to prove it, right, to prove it, you can you can take the ratio, right? You can take the ratio. You can calculate the ratio of these two. So should you take the ratio, or yeah, let's see. Let's take the ratio. If you just take the ratio, so this is again our rough explanation. Okay, this is not a proof. If you take this ratio, then what does it become? It becomes n by this. And now if you just work this out, this becomes root n by root n plus 1. But you see, these two are basically the same things. The square root doesn't change that much when the number becomes big, right? Compared to what the number is. So this is almost like 1. It's very, very less. And because this is almost like 1, okay, it's almost like 1. So if this one, so if these terms are almost like these terms after a certain point, let's say after 100 or something, some number of terms, right? I mean, after some number of terms, this will become equal to, or this will be, after some number of terms, this will be like less than 1, but more than maybe 0.99, something like that. You can, if you calculate terms, you can understand it will happen. Again, it's not a rigorous proof. For that we will need terms like limits and so on, but we just want to develop intuition behind how quantities behave and so on, right now. So it's, since it's almost the same, so basically, I mean, this ratio is between 1 and 0.99, right? So if one of them is finite, the other should also be, summation should also be finite. Let us write that in more details. Let us say that if this is between 1 and this is between 0.99, let's say after some 1000 terms, you can check that with a calculator. You just need a number here, really, that's all. You don't even need 0.99. But in any case, I mean, if this is what you have, then this is what you get. And that's all you need. This is it. Now, if you're adding things in this side, and if this is going to be bigger than adding things on this side, and these guys here are already, bigger, going to infinity, then that should also go to infinity. Let's see the details, a bit more details here. It's like this. So if 0.99 times 1 by n is less than this, and then 0.99 times 1 by n plus 1 after some n, now that n will be 100 or something like that, some n not, after some point, sorry, yeah, like this. Sorry, it will be n plus 1, n plus 2, right? You're putting in place of n, you're putting n plus 1, right? So it become n plus 1 times n plus 2. And like this, you can keep adding. But these things, when you add, they become infinity, because it's some fixed n. Some n is some 100 or something, right? I mean, initially, if you remove a few terms initially, that doesn't make an infinite thing finite, right? So it will remain infinite, and 0.99 times that will remain infinite. And so this will also be infinite. Okay. The moral of the story is that if you take ratios, if you see a series and if it looks similar to some series, then take ratio and see. Ratio of just the terms. That's the magic. Just the ratio of the terms. If the ratio of the terms is between two constants, you just need two constants. If it is a 2 and it was 3, it won't matter. This will still work. Right? It will still work. So that is what it is. Okay. That's why it is finite. So are there any questions? If there is some details which is I need to say more. Yes, that's always correct, right? That's always correct. I mean, if you have an infinite thing and you remove some finitely many things, right? If you have a1, a2, a3, and if you add them, and if this becomes infinite and you remove first 1 million terms, then this is finite, right? This is maybe 10,000, anything, any finite thing. So this part should again be infinite, right? Because the total is infinite. Because the total is infinite, you can take away finitely many terms from the first. From you can take away any finitely many terms. You can divide by any finite number, fixed, fixed finite number, so on. Okay, so that's correct. But then also try to write a proof of this, more maybe convincing. So what I've said is just a rough argument. Okay, what you can try to do maybe is can I don't know if you can really. Yes, you can. I mean, so what I am now asking people is, see, what all I've said is maybe not very rigorous. So either you can try to make it rigorous. Okay, so say that maybe after n equal to 50 this ratio is between 1 and something, try to show that. Or you have another, I think another way which you can try is you can do something like this. You take this n square plus n, and what I'm trying to say is that just basically use some sort of inequality, right? I mean, you can do something like this, maybe n square plus n. Yeah, something like this. Yeah. Huh. So something like that. I mean, it can be done in many ways. It can be done in many ways like this. Yeah, as you were saying, you can do basically. Yeah, you want to just say that this is bigger than 1/n sort of thing, 1/2n, 1 by something like that, right? Yeah. So what you're saying is certainly correct, and you see this will work, right? You take the square root and then you flip the take the denominators. The inequality gets flipped, and that way also you can do. But eventually, the idea remains the same. The idea remains the same, that you have to just figure out a way to compare this to make this bigger than the 1 by n series. Okay, that is really just what the idea is. Yes, so it will work in many ways. Please think about. So you see, these problems have very interesting solutions. Okay, and yeah, soon we will have easier solutions. Maybe when we do limits, and that language is powerful for certain reasons. And even the geometric method we saw, will we be extending that to when we do integrals, integration, using integration to show that such series converge. So that was one. Okay, so I think we have time is up, but we want to just do one more question which I had also asked the last time. Okay, so because I should finish them, otherwise they'll just be left out. Okay, and it's this, uh, one by this and this. Yeah, this question. Yeah, so what happens to these numbers? Do they become infinite or do they remain less than something? Okay, first of all, did I ask this question last time? I think I did. Remember. Okay. Uh, so this is sort of in between, right? I mean, if you call this S3 by 2, then S3 by 2, so this is certainly less than 1 plus this. This is something which I thought about, right? Because, yeah, I mean, because 2 to the power 3 by 2 is bigger than 2. And so 1 by of that is lesser, and similarly for 3 and 4. So this is certainly true. But and also on the other hand, it is bigger than this other series which we had looked at. And once again, for those who have not looked at it, try to prove that this is actually finite. Okay, this is finite. That is thing. Yes. And this is infinite. And that is the problem. So this is in the middle, and it is bigger than the finite one and lesser than the infinite one. So we can't say anything. Can we say anything just from this inequality? Can we say it's finite? Not from here. If it's lesser than some infinite thing, it doesn't mean that it is finite. It can still be infinite. Right? I mean, term by term is lesser, so what? It can still be infinite. And it's bigger than a finite thing, so it can be finite or infinite. We don't know, right? So how do we do this? Oh, okay, didn't give you. Okay, so think about this. Yeah, the idea would just be to use the same method of group and compare. Yeah, I think I explained this the last time, right? Just grouping and comparing with the geometric progression. So you yeah, you group and compare. So this is maybe, let's try to do it now, right? So you do something, maybe I'll remove this part. Okay. So how do you compare this? Yeah. So see this, you can say, so this is less than, this is less, this is just this quality equal to this, and then this is less than 1 by 2 to the power 3 by 2. Okay, so we have put an upper bound on those. Certainly, right? 1 by 3 is obviously less than 1 by 2, so this is true. And then from here up to 1 by 7, and this is the same technique which we had used, right? All these, I'm just cutting it short here because we have seen this. And yeah, seen this. All these are less than 1 by 4 to the power 3 by 2. But how many of them are there? 4 of them, right? 4, 5, 6, 7, 4 of them. So it is less than 4 times this. And here this is 2 by this, and this is 4 by this. And next step, again, fill in the details, please do it. Okay, 8 by this, and it goes on, right? Goes on like this. And so what is this? What is this? If you simplify, this is 1 by square root of 2. This one is 1 by square root of 4. This one is 1 by square root of 8, and so on. So what you see above, the S3 by 2, this thing is less than this. But this is the geometric progression. This is like that r to the power n kind of thing. What is the r? The r is the square root of 2, power 1, power 2, power 3, and we know that is finite. So I've almost done it, but just, yeah, try to fill in the details. Right. So there are no, I didn't really do anything. I not given any problem then. Yeah. Then try to maybe, yeah, we have of time. I should finish on time. Sorry. Just with this question. So it is the thing. This is the question. If you take n to the power r, and you take the summation from n equal to 1 to infinite, so it just means, n equal to 1, n equal to 2, and so on, and r is bigger than 1, then what is it? So any r bigger than 1. We took r equal to 3 by 2. We took r equal to 2, and we showed, right? This just means summation, r n changes. Try to comment on this. For any r bigger than 1, what happens? Okay, just think about it and fill in the details of what I've said, and then that's it for today. We'll next meet on Wednesday. Okay. Okay, for those who are doing the Wednesday class. Okay. There we do. Yeah, thank you. Yeah, just for those who just have not noted it down, just note it down. And if there are any questions for what we have done today, just you can ask. So there are no questions.